Hey everybody, this is a lecture on light and the electromagnetic spectrum. We're going to cover how seeing works, the speed of light, the energy of a photon, and the different types of electromagnetic waves. Let's get started. We're going to start with a question. If you are in a completely dark room with a red apple, and all windows and outside sources of light are sealed, what color is the apple? Now, most people, when they think about this, they're going to say red or black. So think about what you decide to say and why. Now, red or black are both going to be acceptable answers because in the dark room, you're not going to be able to see the apple, so it might look black to you. But obviously, nothing about the apple has changed by you turning off the lights. It's just that you don't see it. And this gives us some insight into how light works and how sight works. When we see something, what we're seeing is light coming from an object, either reflected from that object or emitted. For an apple, we're looking at reflected light. White light, which is the normal light that we deal with, is a mixture of all different colors of light or all different frequencies. So when we shine white light on our red apple, it reflects back red light. And so if that light goes into our eyes, we see it as a red apple. Different colored objects, different pigments reflect light differently, and thus we see different colors. And we can kind of show this up here. If we use 4 different types of light on these different objects, they will look different, even though we're not changing the object. This is white light, so we're shining all colors of light on our 3 objects. With red light, notice the card, we can't even see that it's the 3 of hearts, because it is only reflecting red back. It's going to be reflecting red back on the 3 and on the white part. If we shine green light, everything looks green. If we shine blue light, things only look blue or black. White light is composed of all different frequencies, all different colors of light. Light is one type of electromagnetic wave. An electromagnetic wave is a wave in the electromagnetic field. An electric field is, well, just like a gravitational field is this thing that exists everywhere in space, and it shows you how strong the gravitational force is. The electric field is something that exists everywhere in space and shows you how strong the electric force is. And when charged objects, like an electron or a proton or an atom, vibrate back and forth, they create waves in this electromagnetic field that vibrate out. Different frequencies of oscillation determine the type of electromagnetic wave. Electromagnetic waves are actually transverse waves. This is an illustration of an electromagnetic wave traveling through space. Here in this GIF, we can see our electromagnetic wave traveling along the y-axis. The red lines represent the electric field vector, which we'll discuss later on in the year. And the blue represents the magnetic field vector. And they're always perpendicular to the motion of the wave itself. So electromagnetic waves are transverse waves. Light is very fast, much faster than sound. And measuring the speed of light is difficult. There's a story about Galileo attempting to measure it. He took his assistant on 2 distant hills about a mile apart, and they each had lanterns. He flashed his lantern to the assistant, and when the assistant sees the light from Galileo's lantern, the assistant will flash their lantern. When Galileo sees the light from the assistant's lantern, Galileo measures the time it took for that light to travel to the assistant and back, and the known distance to measure how fast light traveled. Turns out, light travels far too fast to measure this way. So it's not easy to measure the speed of light using just distance over time, at least not over such short distances, because light is very, very fast. Our first semi-accurate measurement of the speed of light was in the late 1600s by a person named Raymer. Now, at this point, astronomy was pretty good, and we had a good idea of where all of the bodies in the solar system would be at any given time. So Raymer was looking at one of Jupiter's moons, Io, and it travels in a circular orbit around Jupiter. And so you should see it in the same location at regular intervals, repeated intervals. Raymer noticed that when the Earth was closer to Jupiter, on the same side of the Sun as Jupiter, Io was arriving a little bit ahead of schedule. And when Earth was on the other side of Jupiter, Io was a little bit behind schedule. Raymer realized that this was because there was a delay in the time it took for the light to reach Earth from these different points around the Sun. And he used this lag between the orbit of Jupiter and the close orbit versus the far orbit to calculate the speed of light. And he measured it pretty accurately, not exactly accurately, but within about 75% of the correct value. He measured 227,000 kilometers per second. It wasn't until the late 1800s that we got a really accurate measurement of the speed of light, and this is a kind of hand-wavy explanation of how we did it. Michelson performed this experiment, Albert Michelson. He was also important for relativity. He sent a light through a rotating strobe disk, reflects some light off of a very, very distant stationary or fixed mirror over here. That light reflects back, but when it hits the strobe disk, because the disk is rotating, it's going to reflect back at a slightly different angle. And you can manipulate that angle difference to calculate how fast that light is moving, traveling here to here. And so we got a pretty accurate measurement of the speed of light then. It's actually 299,792,458 meters per second. That's our speed of light. So that constant, the speed of light in vacuum, is a universal constant, and it's one of the most important constants in nature. So we give it a special letter. It's lowercase c for the speed of light. Like all waves, speed is wavelength times frequency, so if our light is in a vacuum, we can use c equals lambda f. You should write down the value for the speed of light, at least at 3 sig figs. It's a very nice round number to 3 sig figs. C is just equal to 3.00 times 10 to the 8 meters per second. And not only is this the speed of light, 300 million meters per second, it's also the maximum possible speed for any object traveling through space. It's the universal speed limit. And in fact, no object with mass can ever travel at the speed of light. But we will need to study relativity in order to understand why that is and how things behave near the speed of light. We've already mentioned that different frequencies of light determine the type of electromagnetic wave. This is our electromagnetic spectrum here. We can sort our electromagnetic waves by their wavelengths. We have larger wavelengths here on the left side. Or we can sort by frequency. We have higher frequencies over here on the right side. And the order of electromagnetic waves is radio, microwave, infrared, then visible light, ultraviolet, X-ray, and gamma ray. Now, the sorting of these different types of waves is very arbitrary. We've really just sorted them kind of generally based on how they interact with matter. Visible light is defined based on what we can see. But the other types of waves are defined based on how they interact with matter in different waves. Notice that radio waves are very, very large. They can be as large as buildings or as large as the Earth. And gamma rays are very, very, very small, but they have a very high frequency. These little images show you objects that are about the same wavelength as the type of visible light. Now, we can also ask the question, which type of light would you rather have bombarding you? Which would you rather be showered in? Radio, microwave, or gamma rays? And you probably know that you don't want to be showered with gamma rays or X-rays or even ultraviolet rays. That's because these different types of light have different energies associated with them. And this is because light isn't just a wave, it's also a particle. Really, we can treat a wave of light as a stream of particles, which is also called, particles are called quanta. And each particle has its own energy. Different frequencies of an electromagnetic wave have different energies, and each particle of light is called a photon. This is a representation of light as a stream of particles shining from a lamp. This is going to be a reddish-orange color light. Our wavelength is 637 nanometers. We can actually calculate the energy of our particle of light because it's proportional to the frequency. And the equation is the energy of a photon is equal to this constant h times the frequency. We could also write it as hc over lambda just by substituting in c equals lambda f. The energy, of course, has units of joules in our standard units. And to calculate it, we do h times f. H is called Planck's constant. And it's another fundamental universal constant. And so you do need to write down this constant. It's equal to 6.626 times 10 to the minus 34 joules times seconds, or joule seconds. Energy is sometimes written in joules, but for photons and electrons, because the energy is going to be so small in joules, 10 to the minus 34, often we'll use a different unit, which is the electron volt. And this is just our conversion between joules and electron volts. 1 eV, or electron volt, is equal to 1.60 times 10 to the minus 19 joules. It's a good idea to write that down just so you have the conversion if you need to convert. Okay, let's do a few sample problems. An X-ray has a wavelength of 5.00 nanometers. 1, find the frequency of the X-ray. 2, find the energy of a photon of this X-ray in joules. Okay, well, we're given this is our wavelength. We know that the speed of light is c, which is 3.00 times 10 to the 8 meters per second. So we're going to use c equals lambda f to find the frequency. F is then equal to c over lambda if I just divide both sides out by lambda. So it's going to be 3 times 10 to the 8 divided by 5 nanometers. Nano is 10 to the minus 9, 5e minus 9. Plug that into a calculator. Although, probably don't have to because these numbers are so round. We get 6.00 to 36 figs times 10 to the 16 hertz. That's our frequency. We need to find the energy of a photon of this X-ray in joules. Well, we know the energy of a photon is equal to h times f. Since we know the frequency and we know the Planck's constant, we can do that. H is equal to 6.626 times 10 to the minus 34 joule times seconds, and our frequency is 6.00 times 10 to the 16, not 110, just 10. Doesn't want to erase. 6 times 10 to the 16 hertz. And hertz cancels with seconds. We're going to be left with units of joules. We're going to be left with units of joules. We just plug it into a calculator. 6.626 e minus 34 times 6e 16. We get 3.98 times 10 to the minus 17 joules. Very small amount of energy. And one last problem. A photon has an energy of 5.00 times 10 to the minus 22 joules. Find the wavelength and frequency of this light. So let's do E equals HF. To find the frequency, we get F equals E over H. So that's 5 times 10 to the minus 22 over H, 6.626 times 10 to the minus 34. Seven 0.55 times 10 to the 11 hertz is equal to our frequency. And to find the wavelength, C equals lambda F. So that implies that lambda equals C over F, which is equal to 3 times 10 to the 8 divided by 7.55 times 10 to the 11. Plug that in. We get 3.98 times 10 to the minus 4 meters. That's that. Basic calculations for light. So in summary, light is an electromagnetic wave. It travels at a constant speed in a vacuum. That speed is given by c, 3 times 10 to the 8 meters per second. You should be able to calculate the frequency and wavelength of different waves using c equals lambda f. You should know that a photon is the name for a particle of light and has energy proportional to frequency using the equation E equals hf. You should also be able to calculate frequency and relate it to energy. You should know the different types of electromagnetic waves and be able to order them by wavelength, frequency, and photon energy. And you should also know a couple of general applications of each type of electromagnetic wave, even though that was not covered in this lecture. Bye.